In our next example, again using the principle of mathematical induction, what I want to do is I want to prove the following. Let's prove that if x is a real number not equal to 1, okay, so now we can start to write things more succinctly using our set theory notation, which is why I like to do it first. But let's prove that if x is a real number not equal to 1, then we have the following formula. The sum of x to the k, as k goes from 0 to n. Actually, let me use j as our subscript here, and the reason why I want to use j as a subscript is that k is often used as the in the inductive step. So we have 3 variables now. So let's prove that if x is a real number not equal to 1, then we have a formula for the sum of x to the j, and that formula is x to the n plus 1 minus 1 over x minus 1. And this should look familiar. This is the geometric series formula that is talked about in Calc 2. So this is the reason how we know when certain geometric series converge. Anyway, so this is a formula, and we want to prove that this formula is valid for all x not equal to 1. Of course, x can't be 1, otherwise we're dividing by 0. But if x is equal to 1, then the sum is just n plus 1, and there's nothing to do. So that's fine. And so let's see. Let's do this, and I want to prove this. I forgot to say, I want to prove this for all n greater than or equal to 0. So our base case will be n equals 0. So let's do that. So our base case, we just have to check that this is true when n is equal to 0. And if I take the sum, as j goes from 0 to 0 of x to the j, that's just x to the 0. And on the other hand, if I take n equals 0 and plug it into the right side of our equation, x to the 0 plus 1 minus 1 over x minus 1 is just x minus 1 over x minus 1, which is 1, since x is not equal to 1. So these are both equal to 1, and therefore our base case is true. So our base case, let me just write this a little bit better. Our base case is true since this sum, as j goes from 0 to 0, x to the j, is x to the 0, which is 1, which is what we had over here, x to the 0 plus 1 minus 1 over x minus 1. So that's our base case. And again, the base case is usually perfectly straightforward to justify, but it turns out to be necessary. For our inductive step, what we're going to do is we're going to assume that this is true for some k. So assume that the sum of x to the j, so j goes from 0 to k, equals x to the k plus 1 minus 1 over x minus 1. And we're going to assume that that's true for some k greater than or equal to 0. And then we want to show, that, I always like to write out what we want to show. That kind of tells us which direction we're supposed to go. But we want to show that the sum from 0 to k plus 1 of x to the j is equal to x to the, let's think about what happens when n is equal to k plus 1. We get x to the k plus 1 plus 1, so that's x to the k plus 2, minus 1 over x minus 1. So that's our goal. So we want to show that that statement's true. This is an ugly looking j. Okay. Well, the thing that we want to say something about is the sum on the left. So let's look at that. And somehow from this, we want to extract information about this sum, the sum from 0 to k. So we're going to look at the sum from j equals 0 to k plus 1, x to the j. And this is just x to the 0 plus x to the 1 plus all the way up to x to the k plus 1. But think about what this sum is. This sum from 0 to k is really the sum x to the 0 plus x to the 1 plus all the way up to x to the k. And so again, we have sort of this recursive definition going on here. So we can pull out the terms from 0 to k, where those are our exponents, And so let me just put this in brackets so it's a little clearer what we're doing. But this is going to be the sum of x to the j, as j goes from 0 to k, plus the last term, x to the k plus 1. And it turns out by our inductive hypothesis, let me go back, by our inductive hypothesis, we have a formula for this sum. This sum from 0 to k has a nice formula, and there it is. So let's plug it in. And it turns out that the sum from 0 to k is going to have the formula x to the k plus 1 minus 1 over x minus 1. And then to that, we're going to add x to the k plus 1. And so let's just get our common denominator now. So I'm going to multiply and divide by x minus 1. And then I'm going to write this as a single fraction. So we have x minus 1 in the denominator. Let's think about what we have in the numerator. We have x to the k plus 1 minus 1 plus x to the k plus 2 minus x to the k plus 1. If we distribute that x minus 1 over x to the k plus 1. And of course the x to the k plus 1s cancel. So let's cross those out. And that means that we're left with x to the k plus 2 minus 1 over x minus 1, which is exactly what we wanted, and therefore the statement's true for all n greater than or equal to 0.